Hello and welcome to this, the Rethinking the Human Factor podcast with me, your host, Bruce Harris. Now, it's great to have you with us here on the show today. It's especially great because today is the 50th episode of the Rethinking the Human Factor. Now, that's 50 episodes over 4 series and 4 years where we've sort of been hopefully creating a platform and sharing insights to the brilliant guests that we have come on the show, some of whom are from within cybersecurity. A majority of them are from outside of cybersecurity. The thing that they all have in common is that they're absolutely passionate, whether from an academic or a practitioner basis, or sometimes from both sides, about the challenges when it comes to raising human awareness, the challenge of influencing behaviour, and the role that culture plays in that, both as an enabler of those changes, but also something that we're sort of aiming for when it comes to data protection, information security, cybersecurity, whatever you want to call it. So, when I was planning this show, this particular episode, right at the beginning of this year, I was thinking to myself, what is it we wanted to do with this particular episode? What with it being the Big 5-0? And the one thing I really wanted to continue was our absolute commitment at the Rethinking the Human Factor into making sure that every one of the podcasts, it actually produces educational content, things which are going to stretch our listeners' minds, really. And we do that by, getting people on the show, often from different disciplines and topics, but all with some sort of insight into the challenges around raising awareness, behaviour and culture. And the reason why we do that is I'm an absolute believer that if you understand the forces at play, you're better able to then bring around changes in human awareness, behaviour and culture. And this comes very much from, I guess, a principle that I learned from one of the people that I did quite a lot of research into, who basically highlighted that if you don't actually take the time out to investigate the forces at play in relation to anything that you're doing in life, let alone cybersecurity, awareness, behaviour and culture, then you're just a lot less likely to be as successful as you really want to be. So that's what the show's all about. It's all about bringing these guests on, getting them to share insights, and those insights should give you an understanding of the forces at play. Now, this particular episode, the 50th, is all about, I guess, the theory of understanding the forces at play. And when I was thinking about who we could get on the show to do this, I stumbled across a project which is trying to overcome the seemingly unsurmountable. Now, when I read it, I was like, seemingly unsurmountable. This sounds really like some of the feedback I get from people as part of the research that we do and just general conversations I have with people around security, awareness, behaviour and culture. It's like, how can I increase the effectiveness of my efforts to bring around changes in employee awareness, behaviour and culture? It sometimes seems seemingly unsurmountable. And this particular project, this sort of gave me an idea, and it basically led to reaching out to a particular individual who has, for the last couple of years, been trying to address the seemingly unsurmountable. And the seemingly unsurmountable thing that this particular guest has been trying to address is the world land speed record. Our guest is one of the lead designers around the Bloodhound project. And this is a project which has been going on now for many years to beat the land speed record. And I couldn't think of anybody else who was in a better position to be able to explain the importance of, I guess, the principle in understanding that, if you don't understand the forces at play, you're less likely to be able to succeed. And this particular interview is all about understanding the forces at play. So that's what I want you to take away from this particular interview. And I guess that's what we're trying to do at the Rethinking the Human Factor, is ensure that all our listeners have a better understanding of the forces at play, and that you can take that understanding away and sort of improve upon your own great efforts around bringing around those changes within your organisation's employee awareness, behaviour and culture. So, without further ado, let's get on with the interview with Dr. Ben Evans. Hi, Ben. I hope I haven't built you up too high.
Thank you very much. I'm feeling the pressure now. Thank you for inviting me onto the podcast. It's lovely to be here with you.
Oh, it was great. It was absolutely fantastic. And we always like to apply the pressure on, because we know that means you're going to use one side of the brain more than the other side. So I'm more likely to work with those biases and heuristics. So great. Yeah. Now, you're the first sort of aerospace sort of engineering guest that we've had on the show. And I'm sure there are going to be listeners going, where's he going with this? Where's he going with this?
Yeah, I might be thinking that too, Bruce.
You're thinking that as well. Okay, right, fine. All right. I'm sure we'll be able to pull something out of all of this. So, first question we always ask people, or just like into the podcast question. Tell us a little bit about the journey that you've been on, where you're at the moment and the journey you've been on to get there.
Yeah. Okay. So, so my background, my kind of area of interest within academia and research is within aerospace engineering, but more specifically, it's all about modeling aerodynamic flows. So I basically use a technique known as computational fluid dynamics, or CFD is the acronym we use, to try and understand basically how air flows over various bodies, whether that be a car or aircraft. That's basically what I do. So I got into this particular project, Bloodhound, well, actually over a decade ago now. I was just wrapping up a PhD in computational fluid dynamics. Did not in any way, shape or form have my eyes set on designing the world's fastest car. And I was approached by a chap called Richard Noble, who I'm sure many of you will have heard of. He held the land speed record back in the 1980s.
Yeah.
He was the pioneer behind the thrust supersonic car in the 1990s. And he had this mad idea that the land speed record needed to be extended to 1,000 miles per hour. And I took a call that said, basically, Ben, do you want to be involved? The first question
that's a mad call.
It is a mad call. And I didn't see it coming. To be honest with you, at that point in my life, I was thinking, right, I'm wrapping up my PhD. You need to get this thesis finished. I was thinking about becoming a teacher, if I'm honest. Certainly hadn't planned to stay in academia. Certainly hadn't planned to design fast cars. But this just seemed like, it was obviously an interesting conversation I had with Richard. The first question I asked in response was, why? I've heard of the land speed record, don't know a lot about it. Why do we need a 1,000 mile per hour car? And for me, the hook really was twofold. One was, well, here's an incredibly difficult problem that we don't even know if it's possible to solve. Being a part of, a team of people who are going to try and figure out, can we do this? And if we can, how do we do it? Was fascinating, I thought. And also the kind of wider objective of the project, which was to try and inspire more, particularly young people, to take up science and engineering. It is kind of what gripped me, that there was this bigger vision for the project than just how do you make a car go fast. So I kind of naively got involved in the project all the way back in 2007, thinking, maybe this will be 2 or 3 years to sidetrack me from my ultimate ambition of becoming a teacher. And here I am, a decade on, still plugging away at it. I'm based at Swansea University in South Wales, where I'm now an associate professor.
But you're really happy, even though it's like 10 years later. You can see it. Obviously, with people doing the podcast and listening into this, you can't see it, but you clearly enjoy what you're doing.
Yeah, absolutely. And you described it well at the start, that it's been a journey. I didn't set out on this thinking that this was going to be a 10, 11-year project. In my head, this was going to be 2 or 3 years all wrapped up and then move on to a proper job, but we're still plugging away at it for for all sorts of reasons.
Yeah. So I'm going to just pick up on something there, because, when you got that call from Noble and you're thinking to yourself, okay, is this even possible? And there was what is the problem? And the problem being set was a really simple one, is to get a car to travel at 1,000 miles an hour.
Yeah.
Actually, first question for you, can you actually have a car that travels at 1,000 miles an hour? Because I've seen the Bloodhound. It doesn't remind me much of a car. It looks more like somebody's taken a jet off a jet fighter, put a seat at the front.
Yeah.
And this is a really simple engineering description, by the way. And then they've put somebody in who's clearly got some...
Yeah, I know where you're going. Yeah. So first thing I want to say is it is definitely a car. The land speed record rules are relatively slim, which is one of the reasons why I think from an engineering point of view, the land speed record is very, very interesting. It's got 4 wheels.
Okay.
Steered via 2 of those wheels through a steering wheel in the cockpit. Right. Like a conventional car. But yes, you're right. Unconventionally, it is powered by a jet engine and a rocket engine.
So no coffee holder.
No coffee holder, no. But that first question of, well, is this even possible, was a really important one. We basically gave ourselves a year from the tail end of 2007 to basically the end of 2008 to try and answer the question whilst, keeping all of this under wraps. We didn't let the public know that we were working on it. We just wanted to answer that question. In principle, is it possible? Like, do the laws of physics, and particularly the kind of laws of aerodynamics, allow you to take something of this sort of scale across the surface of the Earth at 1.3, 1.4 times the speed of sound and keep it safely planted on the ground? That was basically a year's worth of research.
Okay.
We got to the point towards the tail end of 2008 where, the design wasn't fixed, but we had enough confidence in the models that we'd run to say, well, look, we think in principle this is at least possible.
So in that first year then, you'd had this challenge and you were taking the time out to think through, is this possible based upon what we know?
Yeah.
The laws of physics are something that are well established. It's something that we know, it's not just yourselves that know it. There'll be lots of other people from an engineering, design perspective background and go, these are almost the laws are almost like the standards with which we can look at things. Is this possible based upon these laws?
Yeah.
In some respects, it's like these laws are variables. Are they just set, or are they potentially, they're generally set, but there are variations within those laws?
Yeah, that's a good point. So when I talk about the laws, the laws of science are fixed as far as I'm concerned. Okay. I know, science is a discovery and we're discovering new things about the universe, but the kind of laws that a vehicle like this obeys. So Newton's second law, right? Force is mass times acceleration. That is true for Bloodhound. It's always been true, always will be true. Okay. The way the air is going to flow around the car is governed by a set of equations. Okay, they're called the Navier-Stokes equations. We don't need to know that, but that airflow will always be governed by that equation set. What makes things difficult is not knowing what the right variables to feed into those equations are. Okay, so if we go back to something simple like force is mass times acceleration, right? Right back at the start of the project, we knew roughly over what sort of length of track we would have available to us, in the dream scenario to run this car. That then dictates how fast it's got to accelerate to get from a standing start to its peak speed in the space we've got available.
Yeah.
So that dictates your kind of acceleration target. The variables then are, well, what drives the forces that will be applied to this? Okay, so what kind of thrust can we get from a jet engine in a vehicle like this at, when it's running along the ground? What kind of thrust can we get from a rocket engine packaged into a vehicle this sort of size? The big question I was asking was, how low can we get the drag, the force that'll be opposing those thrust forces, trying to slow the vehicle down? How low can we get the aerodynamic drag forces? Can we get the aerodynamic drag force is low enough to be able to get to peak speed in the space that we've got available? So the laws are fixed, but the variables are at play, if you like. That's what you're trying to predict as the engineer.
Yeah. Okay. So it's always it's like you've got the equations, but then the data which actually goes into the equation is the variable.
Exactly. Yeah. And I think it's always remarkable that, I do all this work and we use, high performance computers to run these CFD models to predict forces. And that's, computationally, mathematically, really, really expensive to get to the point where you've just got the data. But then ultimately, you just plug into an equation that we all learned in secondary school, right? We assemble all of that data. We basically plug it into force equals mass times acceleration. And that's what we use to predict the performance of the car.
Okay. So I think it's really interesting because for the listeners, when this is one of the reasons for engaging people like you and getting you up on the show, is that, the existence of an understanding of the laws at work. And then it's about actually the job yourself and your colleagues is just like, gather the data to put into the laws at work to see, is it possible, in theory, is it possible for us to achieve that land speed record? And for our listeners, it's that I guess the analogy is understanding how people make decisions and judgments. What is the data that goes into that understanding that law? Okay, so that in theory, we can drive changes in behaviour. And that's where I start looking at things and I go, the similarities, completely different context, but the similarity in terms of doing that.
Yeah. And of course, this data that I talk about, what makes all of this complicated and why it's not just an easy yes, most of the questions we ask ourselves, they're not easy yes, no answers, is because there's uncertainty in that data, right? We will have had predictions from the manufacturer of the jet system on what kind of thrust we would get at various speeds, but they're just predictions, right? They're error bars sat on that data. When we run our computer models predicting what kind of aerodynamic loads will act on the car at different speeds, nobody's done this before, right? Nobody's taken a car like this at 1,000 miles an hour across the surface. We've just got computer models that are doing their very best. And, we would like to think that we are, one of the world leaders at doing this, but they are predictions. These are models, right? There's uncertainty in the numbers we're getting back.
Yeah.
And so it's not a simple, well, the data says, yes, this is exactly how the car will behave. These are our best predictions, subject to certain assumptions and error bars, and uncertainty feeds into the entire process. Even though the laws are fixed, because there's uncertainty in the data feeding those laws,
Yeah.
You don't have nice black and white answers out.
No. In many ways, you have to have a data strategy, don't you? Look, there is, the data that goes into the equation. The result that comes out is going to drive our decision about whether or not past year one, we think this is even, it's beyond theory. In theory, this can be done.
Yeah.
But that's depending upon the data. So if the data is in any way inaccurate, then you could end up closing the project at the end of year one on the grounds that our data strategy for, making sure we've got the best possible data, the integrity of the data is as close to 100% as we can guarantee, could have potentially have resulted in you saving 9 years of your life working on this project.
Yeah, absolutely. And of course, that very thing is why, we've designed a car and we've built a car that we believe on paper is capable of 1,000 miles an hour. Now, we've already spent 2 months out in South Africa in the desert testing the car. And, we came back and a lot of people were like, well, why didn't it go at 1,000 miles an hour? Well, the answer is you've got to test this. If you look at the test program we ran back in 2019, pre-COVID hitting, that was all about verifying and validating all of the model data that was feeding in, to our predictions. So we didn't go out there and go, right, Andy, that's the name of our driver. Here's your 1,000 mile per hour car. Put your foot down. Let's see what it can do. Yeah. It was, let's do a run at 50 miles an hour. Let's get all the data, compare that with what the models were predicting. Now let's do a run at 100 miles an hour. We stepped up slowly up to, and the peak speed that we've taken Bloodhound to so far is 628 miles an hour, which incidentally makes it already the third fastest car in the world, just as part of the testing.
Yeah, it's like, that's not slow.
So because there's always this uncertainty in the data, when you take your kind of virtual world predictions into the real world, you've still got to be cautious about what you're doing, right? And sensible and gather more data that's now from the real world that you can compare with your computer model predictions. And that's what the test program in 2019 was all about. It wasn't about, can we get the car to 1,000 miles an hour? It was all about how good are the models that we've got of the car to give us confidence that we can accurately predict forward.
Okay, so it's basically validating the work you've done at a theory level. Is you have a test program to sort of say, are we on course are our theories on course for achieving our objective?
Absolutely, yeah. And I can assure you, Bruce, there was a lot of nervousness on my part. So, the real car in the real world was wired up with sensors measuring all sorts of things, measuring the loads on the wheels, the pressure at about 150 points over the surface of the car. And of course, I'm sat out there in a little porter cabin trying to process all of this data while, Andy, the driver, is out on the desert running the car and sending the data back. And I've spent a decade, convincing everyone that we've got the right design. And of course, there's uncertainty in all of this, right? There's a risk that we got it wrong somewhere. And it was a great weight off my shoulders when we started getting up to the kind of speeds where we knew aerodynamically now things are getting complicated, right? We're at the point where some of the flow around the car has already gone supersonic. We're getting shock waves forming around the car. Like that's when things get quite tricky from an aerodynamicist point of view. And we started getting data that, it wasn't perfect. It wasn't, all our data points sitting on this perfect matching trend line.
Yeah.
But, overall, clearly the CFD modeling that we'd done was giving us a pretty reasonable picture of how this car was going to be behaving. And that's what we were measuring. And at that point, I did breathe a big sigh of relief. And of course, what you've got to do in that situation is, it's not going to be a perfect match. The way things happen in the real world and the way your models have predicted it. And what you always want to be able to is where there is a mismatch, try and explain that mismatch. So there were points where we were getting data and we're like, well, that isn't what we predicted. But when you go and look at the car at that point, there was this thing happening that we could never have predicted in advance. Yeah. Right? So things like particles and dust getting entrained and doing strange things to the bodywork. And, that wasn't in our models.
And that's really interesting. When I first reached out to you and we first had a chat, one of the things that I thought when I started to really think about it was the case of, when you think about, accelerating anything through air, surely the density of the air has an impact on that. So suddenly you're like, okay, so surely you would want to choose someone with a thinner air density. So that would suggest it's higher in altitude. And also density comes from, moisture. And suddenly I was just thinking, I was like, God, to do that, the variables, it's not just, these are the variable data that's coming in. It's like, okay, so actually your geographical location could have a really significant impact upon your ability to achieve your objectives, your goals.
Yeah, absolutely. And it comes back to that, that conversation earlier about like, how do the variables play in all of this? Because there's a compromise here for us from a performance point of view, because the thinner the air, from my perspective as an aerodynamicist, the better, really, right? That means lower drag, less ability to generate unwanted vertical forces, too much lift or too much downforce,
Right.
but poorer the performance from our jet system, right? So you get a benefit in terms of less drag, but a negative consequence of less thrust. And somewhere in there, there's a compromise.
Just to be clear there, for those people that are listening here, what you're talking about is you've got less oxygen being sucked into the air, right. Then it makes it less efficient as an engine, yeah?
That's right, yeah.
Okay, that's all my research done in one statement. Listen, okay. Bruce is blown out. That's the research done. Now he's completely winging it for the rest of the Okay, right. So I think what's really interesting, what I think the listeners should take away from that is how you're applying theory, and you're saying, like, in theory, this should work. Just like for our listeners, in theory, anything around changing awareness, behavior, and culture, in theory, these are the theories. But then you need a testing program where you actually validate that theory and reduce the risk of failure further on down the line. And that's pretty much what the process that you followed there.
Yeah, absolutely. And it's, in a COVID world, we've used the word test lots, haven't we? But it is about test, right? I mean, that is kind of how science works. You have a theory. You might even, and we can do this, we can develop now because of, high performance computing, we can come up with fairly sophisticated models of that theory. But then when you take that into the real world, and for us, it was 10 years of Bloodhound being a virtual thing, right? Like it was quite a big deal for me, having spent a decade of seeing Bloodhound on my computer screen, never more than, a few inches long on my screen. And then one day we're out in South Africa on the desert, and here's this thing 13 meters long, making a lot of noise. And I'm like, wow, this is real now.
Yeah.
We're about to put a human being inside that.
Yeah.
And tell him to go fast. Yeah. And of course, what you've got to do at that point is question everything you've done, right? Not in a skeptical way, but in a good scientific way. We just say, look, we need to remember that this was all based on theory and modeling. We've now got to find out what happens in the real world. And it's never going to match perfectly. You want to try and understand, why it doesn't match perfectly. And that gives you the confidence to push on, and in our case, go faster. And for us, going faster means there's more risk involved, right? That the faster you're going, the greater the consequences of if something goes wrong.
Yeah. So I guess we'll take a step back, but I think about, all that validation, all that testing against the objectives. From a design perspective, the importance of getting the objectives very clear right at the beginning, so that everybody's using the same language and they understand that what that language actually means.
Yeah.
Okay. How important is that?
Yeah, I mean, this is fundamental. And it's something that I get to teach now at the university, and I teach aerospace design. And one of the things I am banging on about with students all the time is, what are your mission objectives, right? So, every year we have classes of students coming through designing airplanes. Yeah. And it's very easy in that design process to lose what was it you were trying to achieve back at the start. So for me on Bloodhound, not knowing an awful lot about the land speed record, right? I knew it was about trying to get cars to go as fast as possible. Yeah. Early on, I had to establish exactly what are the rules, right? The FIA is the organization that kind of governs the world land speed record. And, I had to establish that this vehicle that we were designing needed to have a minimum of 4 wheels. That was one of the rules. It had to be steered by at least 2 of those wheels. Okay. Actually, it wasn't the peak speed that gets measured as your land speed record. It's your average speed over a mile.
Oh, right.
And you have to do that measured mile in 2 directions within the space of an hour. Okay. I guess that's so that, if there's any kind of winds that might be affecting the performance of the car, they get cancelled out.
Yeah, that makes sense.
And the objective is, what is the maximum average speed we can achieve in 2 directions over that measured mile with a vehicle that's got 4 wheels, driven by a human being, steered by at least 2 of them? Like that's the mission objective.
So there's like five main things there, I think, wasn't it?
Yeah, which is remarkable when you compare it to other areas of motorsport like Formula One, where you have a lever arch file full of rules and regulations and constraints, which ultimately is the reason why when you look at the grid of a Grand Prix, basically all the cars look the same because of the number of constraints that are being applied upon them. The beauty for me as a kind of creative designer engineer with the land speed record is, if you look at the history of the land speed record, the cars all look fundamentally different, even though they were all trying to do the same thing. They were all trying to go as fast as they could over a measured mile. Yeah. But because the number of constraints placed on what we can and can't do on the land speed record are very limited, actually the number of options for how you solve that problem are maximized. Yeah. So nailing those mission requirements is, the most important thing right at the start of the project. There's a famous story that I tell my students all the time about, during the 60s and 70s and the space race, that obviously the Russians and the Americans needed their astronauts or cosmonauts to be able to write in space. And NASA set their engineers the problem with the mission objective of design a pen that will work in space. And they spent millions and millions and millions of dollars developing what I think then became the ballpoint pen, I think that's what they ended up with, basically. The Russians said, design something that will allow me to write in space. And they decided, well, let's just take a pencil, right? So it's, it might sound trivial, nail your mission objectives, like spend time clarifying what they are and what the constraints are. But actually, subtle differences in how you define the mission objectives at the start of your project can fundamentally change the trajectory of the project. So for us, that was really important at the start. And me, not knowing a lot about the land speed record, it was really important.
Yeah. Okay. When it comes to those objectives, is that something the designer, the person that's sort of architecting the whole thing, should be involved in? Or should that be done by a different group of people and then you get given, like, this is the brief? In effect, I just wonder whether there's any bias that gets exchanged as that's involved.
Yeah, that's a good question. I'm not sure there is any one standard way of doing this. In other projects that might be commercial projects where you've got a client, obviously that's driven a lot by the client. In the case of the land speed record, essentially the FIA who govern the record dictate that to us. The question then of how do you keep track of whether or not what you're doing as the design evolves is meeting those mission requirements, an interesting one. Is that the job of the chief engineer fundamentally? Is that the job of everybody on the design team? How does that work in practice is an interesting one. And I think it is something you've got to be conscious about. It's so easy to get lost, particularly, when you specialize in an area of the design, as is the case on most complex engineering projects. You specialize in my case in aerodynamics. Other people specialize in the structural design. Other people specialize in the hydraulic systems. And it's very easy to get lost in that. And I think every now and again, just going, right, here's our pause point. This is where we're going to update everybody on the team of kind of where our bits that we're responsible for lie in the context of reminding ourselves what we're trying to achieve here. I think it is really important.
Well, I guess if you don't do that, then there's the potential you get so far down the line, and then there's actually a conflict. What you described, for example, the conflict between what you need from the airflow perspective. There's your requirements from an aerospace design, airflow perspective. And then there was I need the air to come through and it's got to carry oxygen.
Yeah.
And the sooner you have you bring those two stakeholders together to identify the potential clash, the less likely are that you're going to invest a huge amount of time, and get down the line and then suddenly find that this isn't going to work together, and then end up you're re-engineering all the work that you've done. It's just like lost time and the costs that are associated with that. So having those updates relatively regularly, I imagine, helps you achieve your goals quicker.
Absolutely. And it's why we are, your university, we often remind our students that actually fundamentally engineering, and certainly aerospace engineering, is a multidisciplinary, subject. You can't really get away anymore with just going, I am an aerodynamicist and nothing else. That's what I specialize in. But I need to know stuff about, engine systems and jets and material selection and structures and suspension systems to know what potential impact there might be on the work that I'm doing on those other areas of the project, and who I need to be speaking to at various points because what I'm doing might impact them. It's very tempting just to go, well, I'm responsible for aero, that's all I'm going to think about. It doesn't work if you treat it like that.
Yeah, I think it's almost like you need to know enough to know when to engage somebody who knows the stuff.
Yeah, absolutely. That's right.
Yeah.
I might not be a material selection expert, but hopefully I know enough about that to be able to engage with the conversation when that conversation comes up in the design meetings, right?
Yeah.
The other thing that inevitably happens when you proactively revisit the mission objectives throughout the design process is you realize that, even if you're starting off with a simple mission requirement, the subtleties quickly come out, right? So for me, the good example of that is, when I took on the role of kind of leading on the aerodynamic design. My biggest concern, as you can probably imagine, take a car to 1,000 miles an hour, is how do you keep it on the ground? Like, that was what was going through my mind. Can you keep a car like this on the ground? And it quickly became apparent to me that actually that's not the problem. You know, when you're traveling at these kind of speeds, you could stick a couple of great big wings on this thing and angle them down and generate a whole load of downforce. You know it's never going to take off with those wings angled as they are. But the problem then you have is you generate so much downforce that you would drive the wheels into the ground, and you've got the world's fastest plow, not the world's fastest car. So as you develop the design and think more about it, the objectives become a little bit more subtle. And actually it became, well, can we manage the vertical loads on the car in a set of limits that we had to define, rather than can you keep the car on the ground? That's the simple problem. Can you keep it on the ground? Well, yeah, that's easy. Question is, can you control the loads to within, some finite bounds? Yeah.
So in many ways, you sort of have assumptions, and then in the process of working through the project, you start to see maybe uncomfortable truths around those assumptions. So you're like, look, what's this actually based upon? And you start to see things differently. You go, oh, actually, we think that's a problem, but actually, this is more the light is being shone on this. And in some ways, I mean, Donald Rumsfeld uses the phrase, or you use the phrase, there's like known knowns, there's known unknowns, there are unknown unknowns.
Yeah.
And I think this applies beautifully to so much actually. But it's in that case, you go, the assumptions are, they're not known knowns, they're known unknowns, because you're just assuming.
Yeah.
Yeah. Whereas it's the science says this is a known known, the formula.
Yeah.
Okay, then there's the assumptions, and then there are the unknown unknowns, and those things only become known once you start working through the project.
Yeah, so for us, a good example of the known unknowns is the uncertainties in the data that goes into the equations, right? Like we know that when we get data from a computer model, that is a good prediction. It's the best prediction we could have without building the car and running it. But there is uncertainty there. And that's what we've got to go out and test and learn about. And the other thing inevitably that happens throughout the process of designing something complex like this is the constraints evolve.
Constraints, what do you mean by that?
So, the mission objective is take a car as fast as you can across a measured mile, right? And initially there's a fairly small number of constraints. Things like the car must have 4 wheels. There must be a human on board the car.
Okay.
2 of the wheels must be used for steering, your design constraints. But then you realize as you start thinking about, okay, so practically, if we're going to take a car at 1,000 miles an hour across a measured mile, and it's then going to take us 4 or 5 miles to get the car to slow down, and we've got to turn it round to get it back through that measured mile within an hour. So then all of the practicalities related to
just turning
how do you turn the car around at the end of the track and refuel it, and how does that work in practice? How does that influence what we can and can't do in terms of the design of the car?
Yeah.
Things like that start kicking in. What kind of turning circle is this thing going to need if we're practically going to be able to turn it round at the end of the track and face the opposite direction and run it again?
Or do we just lift it up with the crane and turn it round?
Well, yeah, exactly. Or do you have these other options of how you turn it around? That, things like, okay, so if we're going to be generating that much thrust from a rocket system for that long, here's how big the fuel tank is going to need to be.
Yeah.
Ben, you haven't made the fuselage, the body of the car big enough for a fuel tank that side. It needs to get bigger. The constraints evolve all the time.
Yeah. Okay. Right. So we've been talking very much from an engineering perspective, but only something that you've highlighted is that this isn't really possible without there being a team. So you can design it in isolation with your computer, and you're looking at here it is on the screen, and you can apply models to that.
Yeah.
But really, at the end of the day, it's about bringing it all together, isn't it?
Yeah. Yeah. And for me, this now is what is really exciting about kind of my area of research, because historically, certainly in the context of aerodynamic design, which is what I've been involved in my career, there have been kind of 2 camps. There's the old traditional camp of we'll run some CFD models, or maybe do some wind tunnel testing, gather a whole bunch of data.
Hold on, let's be clear, because you've used that CFE a couple of times. I just want everybody to know what CFE means.
So CFD is computational fluid dynamics.
Okay, right. Okay.
So think of that as virtual wind tunnel testing. Okay, so we're doing wind tunnel testing inside a big computer, basically. Yeah. Okay, and then the way that's largely the way we design Bloodhound, right? So we would run these virtual wind tunnel tests, or CFD. I'd gather a whole load of data. I would, in practice, what I would do is turn that into a PowerPoint presentation, because that's what we do. And we'd arrange a meeting with all of the other engineers. I'd present the data. We'd sit around a big table and spend all day drinking a lot of coffee, trying to figure out, well, what does all of this mean? How does that impact other aspects of the design? How does the shape need to change as a result of that? And it'll be, a bunch of people sat around a table having that discussion. We'd leave the room, ideally, having not fallen out and agreed on. Right. So the back part of the bodywork is going to have to taper a little bit more, or the fin needs to get bigger, or the rear wheels need to go further out, these kind of things. But at the same time as that, there's been a lot of work, particularly in academia, looking at computational design optimization, right? So you give a design problem to an optimization algorithm embedded in a computer system, and you let the computer solve the problem for you. Okay. And that, and those kind of methods are getting used increasingly in an industrial context as well. But those two parallel kind of approaches to design really haven't connected together as of yet. What I think is interesting, and I think possibly is kind of, how the world is going to change in terms of engineering design in the future, is coupling together computational design optimization, where you've got a computer testing things really, really quickly, using, fancy algorithms to do things really quickly. But the risk of that is you throw away all of the wonder of human intuition and experience and being able to, in principle at least, think outside the box. Right? Sometimes it's referred to as human in the loop optimization. We run optimization problems in a computer, but we've also got human input feeding into that process. And how do we mesh those things together? I think is going to be a fascinating evolution in the future.
Yeah. It's like the human provides the context to what's going on at an algorithm level. There are certain aspects. This is really interesting from an AI perspective within our industry. People are talking about AI and how it can potentially lighten the load on humans, can do things a lot quicker than humans are ever going to be able to do. Then the question gets raised, what is it that humans add?
Exactly. And I think, in a whole range of contexts, I think this conversation has started to happen, or at least should be, is, AI, or however you define that, is amazing, right? Like that expression you use, it lightens the load, right? Like that's essentially what, employing computers to do stuff for us does. But if we just outsource our problem purely to an AI system, what do we lose by removing the human from it? My sense is you lose a lot. Okay, because as amazing as AI algorithms and optimization in general can be, the human brain is an incredible thing, and its ability to kind of intuitively solve problems and see things that perhaps as a design is evolving that a computer couldn't ever hope to see, I think shouldn't be thrown away.
Sometimes when it's almost like a really simple analogy is it's the ability to break rules.
Yeah, exactly. And ultimately, we design things for people, right? We design, whether it's a land speed record car or, the next Tesla electric car, ultimately it's human beings who interact with these things. Yeah. And, as we design these things, what we as humans want from them, that might be evolving as well. And a computer system, as clever and as quick as it is, can never keep up to date with that.
Yeah. To go back to the team aspect of all of this. Yeah. So is the Bloodhound team just a UK venture, or is it sort of global in its scope?
Primarily a UK-based team. There are certain aspects of the project that we brought in expertise from overseas. So, for example, the rocket system that is in development at the moment for it brought in a company called Nammo, who are based in Norway. They developed the rocket systems for the European Space Agency, so they seem like pretty good people to get to get involved. But broadly speaking, it's a British venture. Yeah.
Right. Okay. And do you find when you bring that team together that different subject matter specialists have there's a culture, there's the general UK culture. Okay. So everyone go, okay, it's when people talk about culture, I think an organizational culture or a national culture. Do you find that different aspects of the team almost have different values, attitudes, beliefs based upon possibly what it is that they're doing as for the team?
Yes. Yeah. And I think the biggest differentiator that I have witnessed the team has evolved over the years. It's kind of grown and then it's shrunk at different points in time. I mean, there probably over the decade been 50 plus engineers involved in this project. And typically we've come from one of three backgrounds, or maybe four if you include academia, right? So there are kind of university academics like myself. There are people from primarily aerospace backgrounds. So, the aerospace industry have come to us from Rolls-Royce or whatever. And we've worked closely with Rolls-Royce on the project. People from a motorsport background, and then also people from the military. That's been interesting. So as we move towards kind of the more operational side and vehicle testing, that's when we're like, well, this is now basically a military operation. And we brought in, some incredible support from the military. And you do get, clearly cultures develop within those sectors, bring the people together, there's the risk of clash. And I think this kind of links back, I guess, to, again, why mission objectives is so important and revisiting them is because that's the thing you can unite around, right? For me as an academic, right, my mindset is, create new ideas, share them with the world, right? Like I don't think in terms of how do I make profit off of this. That's not like the way I'm wired. My wiring is we need, think as broadly and as outside of the box as we possibly can. If we have some great ideas, develop some new technology, we share it with the world. I teach it to students. I write research papers on it and publish it in research journals that everybody can read. Like I want to get it out there. And of course, if you come from a motorsport, we've got engineers on the team who've come from Formula One. It's the polar opposite view, right? If they come up with an idea that they think could give them a competitive advantage, it's cover this down, cover it up. Nobody talks about it, right?
Yeah.
So it's just little things like that are kind of culturally different. And, and also organizationally different. A university is a very kind of flat, fluid structure organization. Line management is a bit of an ethereal thing within a university. Whereas within the military, right, it is structure, hierarchy. If my superior hasn't commanded me to do this, I don't do it. I'm exaggerating, right? But so there are differences, but what unites us is the regular reminder, what we're trying to do here is break the land speed record. Like that's why we're all sat around this table.
Yeah, I think that's really important because I've seen that in so many projects where if the stakeholders haven't been involved in defining the objectives, and if we don't share a common understanding of the language we use to define the objectives, and we start to go off course. Sometimes that's because although we don't understand, we haven't done those things, and sometimes it could be even when we've done that, maybe isolation. Working away from COVID, for example, people are working, they're very isolated. Maybe it's just a matter of time, and we sort of forget. Who goes back to the project documentation at the beginning when I'm 2/3 of the way through? I'm busy doing this stuff. So there can be lots of reasons why we go off track, and there are lots of reasons why. For me, these are variables. The stakeholders have different values, etc., at different stages in the project potentially, and they come into conflict, and that conflict then gets in the way of making progress against the actual overall objectives. And you have to bring people back to, look, we might disagree on this. Yeah. You might prioritize this over that. Yeah. Okay. But you're right. If you've got a clear set, it's got to go, but these are our goals. So we've still got, these are the same goals.
Yeah.
So,
in relation to conflict, my experience on this project has been that inevitably there will be conflict in the sense that, two different people on the team might have a different idea about the best way to solve a particular problem. What is key to resolving that conflict and allowing everybody to move on to the next stage is making sure that why a decision has been made is explained well. So I think as long as people understand, okay, that isn't how I would have done it, but it has been explained to me that we've made this decision because of X, Y, Z. Yeah. That's the thing that allows you to move on. And of course, in that, communication is really important, right? When people feel like they've been left out of the loop and a decision has been made and they didn't understand why the decision was made, I think that's when you're at risk of conflict, stifling the project.
And the why is almost like, this is the theory and this is the data we've got to back that up based upon our testing today. Or it's the case, this is the theory. And then people say, well, have you got any data? And you go, well, no. So let's test the theory to see whether we can generate any data to actually validate the theory, which is the point that you made earlier in our conversation today.
Yeah, absolutely.
Yeah. Okay. Right. I just love doing that. There was part of me as we're talking, there was going, this is stretching my head.
I'm glad.
But that's why I do this, because I like to be challenged. I like people to put things in a very different context, and for me to try and work within that different environment that you've been talking about. So I'm tempted to finish the interview here, but I'm going to ask you a question because I think it's really important. And I know that it's a big thing for you, is the making this all accessible through your outreach activities.
Yeah.
And over the years, I've interviewed some people who are really super keen on making insight accessible to people. And I know that part of what this project was about inspiring people from science, technology, engineering, mathematics type of backgrounds, I imagine, as well. How do you think that's going in terms of that inspiration side of things? What do you think it is about a project like this and that is going to inspire the future generation to engage with STEM?
I'm glad you've brought it back to this, because for me, I mean, this kind of comes back to, well, ultimately, overarching everything we've discussed is like what motivates me to stay involved. I don't have to carry on with this project if I didn't want, I could have walked away from this years ago, right? When things got tough. Obviously what we've talked about today is, technically, how does it work? What you have to think about when you're designing the car and so on. But what for me is really important is what has motivated me to keep plugging away at this project. And it is that broader objective of, this is something that I have seen with my own eyes inspires people. Like this is something that, kids and adults do get excited about. What is exciting about it is that there's still that unknown element, right? We've got this objective of, we've designed a 1,000 mile per hour car. We still don't know whether we're going to be able to do it or not. We still don't know if that ambition was too great or how fast it will be able to go. And I think that is one of the hooks into this, like when I go in and run outreach projects in schools and so on, it's healthy, as a professional engineer who's, worked on this for a long, long time, to get up in front of a 12, 13-year-old and say, look, we think we've designed a 1,000 mile per hour car. We don't know that. That's still part of the journey. And you can come with us on that journey, right? You can follow the project. We're going to make all the data that we're getting from the car available to you. We're going to, package things up into a way that's accessible for your school teacher to explain physics and maths lessons.
Yeah.
And come on the journey to find out. You're going to have these questions answered in real time, just as we're, learning the answers to the questions as well. And I think that's exciting, that we're doing something primarily because it's really difficult. I mean, that's ultimately, right? It reminds me of Kennedy, right? When he was asked, why put man on the moon, and he said, we do these things not because they're easy, but because they are hard. And it's the same with this. This is a really difficult thing to do for all sorts of reasons. Aerodynamics is my biggest concern, if you like. But financing a project like this is equally demanding, right? Will we ever get the car to 1,000 miles an hour, or will the finances ultimately dictate that we can't take it there? So yeah, I just think the fundamental challenge of this is the real hook.
I think I guess it's a nice way to sort of maybe to tie things up. And I think for the listeners, when I listen to you, and obviously we've spoken before as well, it's the challenge bit.
Yeah.
It's the sense of, people say, well, is this possible? And then say, well, it's possible, but it's going to really take something. It's not going to be easy. Okay.
Yeah.
But we shouldn't let the difficulty of the challenge put us off having a go.
Absolutely. Yeah.
Yeah. And I think that, for me, there's a key thing there for our listeners. The difficulty of trying to, from a cybersecurity perspective, raise awareness and influence behavior and embed what we cybersecurity values and all those sort of things into everyday culture. We know is incredibly difficult.
Yeah.
But if it was easy, it wouldn't really be worth doing.
Yeah.
Ultimately, it's the whole thing my dad once told me. So on a personal level, his point was that the stuff which is easy to come by is not the stuff that's really going to make you think, wow, I've done really well here.
Yeah.
I've really achieved something, and we've really pushed the boundaries or something. And that's what you're doing. You've set the target, you're pushing the boundaries, you're trying to go past, you're asking the question, can we do better?
Yeah.
And then you're like saying, and what does better look like? And then this is how we're going to get there. Applying theories, things that but also ideas you have, testing them through, okay? Yeah. And it might be that the theory doesn't fully materialize, but you get data. And it might be that the theory actually turns out to be, is completely defunct. The data says that theory doesn't work. And you go, but at least now I know. That's one less thing. I can tick that off the list for any other future projects. We just don't play with that. Yeah. And it saves us time and effort.
Yeah, and all of those things you say there is why ambition is so important, right? I often use the phrase ambition is critical. Like, this is a project, we have an ambition of taking a car to 1,000 miles an hour. We still don't know if that's achievable or not in reality, but that's not the point in many ways, right?
Yeah.
Because, it sounds a bit cliched, right? But the journey you go on in trying to achieve that ambition spawns so many other good, positive things. In some ways, it doesn't matter whether you actually get the car to go 1,000 miles an hour or not, right? We've learned so much along the way, and those lessons are now spilling out into other projects that actually, potentially will affect people's lives in a real sense, and will have inspired hundreds, thousands of, in my context, particularly young people I'm interested in. I want more young people to go into science and engineering. And the project has been doing that over the decade that it's been running.
Yeah. I've really enjoyed having this conversation.
I'm glad.
Hi there. Well, I hope you enjoyed that conversation I just had with Ben. He's really, really, really nice guy. I remember all the conversations that we had in the run-up to it. He was so really up for it, and that energy really, really comes across in the interviews that we just have. You know, when I first did the intro to this, I probably went on about it for a little bit too long, but for me, the real value in listening to Ben comes back to this, you know, what's the seemingly unsurmountable challenge of breaking the existing land speed record. You know, what he's doing in so many ways is looking for, you know, marginal gains across a whole wide variety of different forces at play. But the important thing is, you know, Ben has to understand what those forces are. Then he has to find ways of improving how you handle or leverage those forces to achieve the outcome. Now, in Ben's case, the outcome is all about speed and doing it safely, and being able to do it in a way which achieves the rules which mean that you get a world record. And I don't see a great deal of difference in terms of how we, you know, the management approach to addressing the human factor as well. You know, a lot of the interviews that I've done over the last 50 episodes have all been about people explaining the forces at play when it comes to human awareness, human behaviour and culture, and how by understanding these different forces at play, you can either sort of like work to mitigate, to manage those, to reduce those forces if they result in a negative impact upon your efforts around employee awareness, behaviour and culture. Or, as is often the case, we actually have opportunities to leverage these forces to be more effective in our efforts to bring around those changes that we all desire when it comes to cybersecurity and good, positive security behaviours. So I think that's, for me, what comes from this, the insurmountable, the seemingly insurmountable challenge. You start to tackle it by breaking it down and understanding the forces at play. When you understand the forces at play, you can manage those forces, or you can leverage those forces to increase the likelihood you're going to overcome the insurmountable. And that's the core thing I really wanted to get in this 50th episode of the podcast across to you, is that to be successful when it comes to employee awareness, behaviour and culture, you truly have to understand the forces at play. Now, one way you can understand the forces at play is to carry on listening to the show. We've got the next series pretty much already scheduled, and pretty much already all the interviews are done. So that will be coming out in 2022. Best way to make sure you don't miss any of those out is to follow us on Spotify, Apple Podcast, or go to the www.re-thinkingthehumanfactor.com/podcast page on our website, and you can follow us there. Now, if you've been listening to the show and you're thinking, hey, do you know what? Actually, I really like the idea of understanding the forces of play and how that actually might be something I can leverage or I can manage to make sure that, you know, my efforts within my own organisation are as successful as they can be. Well, the good news is we do train. I do training specifically. I do training to enable people to understand what those forces are and how best to leverage them in a structured way. And that ultimately, when you finish that training program of 4 courses, you will achieve the certified human factor architect status, basically demonstrating that you as an individual can architect working environments which increase the likelihood of compliance, and you do that by better understanding the forces at play and using those as design principles within that working environment. If you'd like to know more about training that we do for 2022 and 2023, then please visit the re-thinkingthehumanfactor.com/training webpage and sign up to the webinar, where I will spend an hour sharing with you sort of insights that have driven different approach to how we design syllabus and how we deliver our courses, and what we think are the potential value that you can get from those as well. Anyway, it's been great to have you here with us for the 50th episode of the podcast. It's been an absolute pleasure and an absolute privilege to actually spend time with my guests. I think one of the things that really come from doing these interviews, especially with those people who don't come within cybersecurity, is that I've really enjoyed talking to some really influential people who really know their subject matter really well, and helping them understand, helping increase their own awareness of why what they do is relevant to the challenges that my listeners, that's you, face day in, day out when it comes to cybersecurity, awareness, behaviour and culture. Thanks for listening in. I hope you can join us for the next 50 episodes. Until then, carry on rethinking the human factor.